Last time we looked at forests, and now we're going to see how the facts that we know about forests can help us prove that Kruskal's algorithm for finding a minimum weight spanning tree of a graph always works. So remember, this was an example of a graph that we had where we have weights on each of the edges, and our goal was to find a way to traverse the graph in a tree, so no cycles, such that we touch every vertex. That's going to be a spanning tree, and we have a minimum weight associated with it. Okay, let's prove that Kruskal's algorithm always works. So oftentimes for proving that an algorithm works, there are two approaches. Either it can be constructive and you can show, well, this definitely did it, or it can be by contradiction, assuming there was something better and find a contradiction. That's the approach that we're going to take this time. So we're going to suppose that Kruskal's algorithm finds a spanning tree T, okay? And we're going to order the edges of T. Let's say the edges of T are going to be T1, T2. There are n vertices, so we know there are n minus 1 edges. And let's order them in such a way that we have that the weight of T1 is less than or equal to the weight of T2 is less than or equal to, and so on and so forth. We can always just order them in this way. Okay, so those will be our edges. So for example, if this was our tree, we could say maybe this is edge 1, edge 2, edge 3, edge 4, 5, 6, 7, 8, and 9 is a perfectly good way to do it, as long as we put all the 2's before all the 3's. Okay, now we're going to try for contradiction. So suppose for contradiction that there exists another spanning tree. We'll say U, and we'll give it edges U1, U2, all the way up to UN minus 1. And we want to order those in the same way. So weight of U1 less than or equal to weight of U2. Now, some of the U's might be the same as the T's. I'm not saying they're not. I'm just saying that we've got this situation, and this is a spanning tree. And if I add up all of the weights of the U's, so the sum over all I of the weight of Ui, so I here is going from 1 to n minus 1, suppose that is strictly less than the weight of the spanning tree that Kruskal's algorithm found for me. That was the weight of T sub I. Okay, so that would mean that since this has a strictly smaller weight, this would mean that this is not minimal. It's not a minimal weight spanning tree. Okay, so that's what we're going to suppose. And we're looking for a contradiction, okay? And I've put this ordering on my edges of my tree so that I can take advantage of the fact that the algorithm works by taking one edge at a time. And the algorithm, Kruskal's algorithm, would pick, you can always take this to be the first edge that Kruskal's algorithm found. This is the second edge that it found, because it's always finding the minimum edge at every step. So by the Kruskal's algorithm, we know that the weight of T1 has to be at most the weight of U1. Because the way Kruskal's algorithm starts is all edges are in play, and you pick the smallest weight one. So whatever the smallest weight thing is for you, it can't be bigger than the smallest weight. It can't be smaller than the smallest weight total. Okay? Great. So now I'm going to need to get some more information in here. So I'm going to choose, this is where it's going to get contradiction. So choose K is going to be some number, minimal, such that the weights flip. So I'm thinking here as the partial sums of the weights. So if I take all the weights and add them up together, then U is less than T. But here initially, T wins. So I'm going to take K to be the minimum time where I get that the weight of T1 plus all the way to the weight of TK, those first K things, the first time it's strictly bigger than the weight of U1 plus the weight of UK. So let's think about that and make sure that it makes sense. So because of this fact, this tells me that K has to be bigger than 1, okay? And this over here tells me that k has to be less than or equal to n minus 1. So therefore k exists. It's some number between 2 and n minus 1. Okay, great. So now what? How does that help me? Well, now I'm going to consider a forest. Actually, I'm going to consider two. Consider two forests. So one of my forests I'll call F. And what is this going to be? It's going to be the forest that has edges T1, T2, all the way up to TK minus 1. Since K is bigger than 1, this makes sense, okay? And this is a forest because T is a tree. I've taken a subset of the edges, so this is sort of a subset of the tree. So it's going to be a forest. It might not be connected, but it might be connected. And what's the other one we're going to take? The other one we're going to take, let's call it P. This is going to be the partial sums, the partial edges of the U's up to K minus 1, but actually I'm going to throw in one more edge. So this is also a tree. So I'm allowed to throw in all the edges, which may be what I do, but I throw in one more edge for P. Now what? Now, remember that lemma. We had a lemma that said, given two forests, P and U, okay? Two forests, P and U. Here are two forests. Okay, the number of edges for, F and P, the number of edges in F is strictly less than the number of edges in P. Well, that's true. The number of edges in F is K minus 1, and the number of edges in P is K. There exists an edge in P that we can add to F. Okay, so we're going to use this lemma. This lemma tells us that there exists some edge UI, but for here for I equals 1, 2, all the way up to K, such that F union UI is a forest. Okay, that's what the lemma gets us. How does that help us get a contradiction? So when we're looking back at this, what does this mean? Well, think about the weights. So it's not a cycle. So what's the weight of UI? Well, because of the way that I've ordered my weights here, it's less than or equal to the weight of UK, right? Because here K is the last one, and I picked some, so it could be UK that I picked, but it's certainly before this, so this one is the biggest weight out of all of these. So this is certainly true just by the way I've ordered my weights. But what else do I know about UK? Well, keep in mind that K is minimal such that I flip this inequality so that means that in particular, maybe I'll write this statement down, that if I had the weight of T1 up to the weight of TK minus 1, this would have to be less than or equal to the weight of U1 up to the weight of UK minus 1. Right? That's what it means for K to be minimal. It's the first time it happens. So because of this statement, right, that means that, well, what do I know? That means that the last thing added had to have been the one that flipped the boundary. So in particular, this is less than or equal to, well, actually strictly less than, in order to flip that inequality, the weight of TK. Otherwise, I didn't choose the right K because the only way I could flip this inequality is if the thing that I've added over here is bigger than the thing I've added over here. Okay, where is my contradiction? What does the algorithm say? The algorithm says, among all the edges that create no cycle, this creates no cycle, choose the one with minimum weight. But this edge that I did not take is strictly less than this edge. So UI is not in F, right? We didn't take it already. It's an extra edge, and it's strictly less than the one we take. So this contradicts how Kruskal's algorithm works. So that is our contradiction. That's how we know it really worked, because we get the contradiction by there's some edge we didn't take that's better than the edge we did. So for T, we must not have followed Kruskal's algorithm. So that's our contradiction. So Kruskal's algorithm always helps us find a minimum weight spanning tree for a graph. Now there could be more than one minimum weight spanning tree, But they all have the same minimal weight, so one is as good as any other.